No, okay, good. So what we did last time was we saw the proof that we started looking at the proof that the post-correspondence problem was undecidable. But in order to do that, what we showed was a reduction from ATM, right? But instead of reducing directly to the post-correspondence problem, we reduced from this variant, MPCP, right? And that was exactly like the post-correspondence problem, except that a set of dominoes was an MPCP instance if there was a matching, and that matching started with the first domino, right? Because in regular PCP, it could just be any matching. Yeah? This all sounding familiar, hopefully? Any questions about anything I can clarify from last time? Yeah. Well, maybe subset's the wrong way to think about it. It's like it's PCP with an added constraint. So intuitively, it should seem a little easier to solve, right? No, so a matching has to start with the first or designated domino, right? And that wasn't the case in regular PCP. Yeah? Cool. Any other questions? I think it's about time, actually. So, all right, set your clocks, ladies and gents. This is going to be one fast lecture. Yeah, so it was pretty clear from my office hours on Friday that people were still kind of unclear about certain elements of, what we were doing on Wednesday. So to kind of just write down what we did last time, we showed that, oh no, okay, all right, cool, very cool. Is this, I get the little, there we go, nice. Yeah, so last time we proved that this variant MPCP was undecidable, right? And in order to prove that, we gave a mapping reduction from ATM, and it was computed by this Turing machine R sub MPCP. Yeah? Because a mapping reduction is a function that maps instances of one problem to instances of another problem such that membership in the language is preserved through the mapping, right? But in order for it to be a mapping reduction, we need to have some Turing machine that computes it. And that's what this R sub MPCP did, okay? So the way this mapping reduction worked was as input, since it's a reduction from ATM, it accepted an ATM instance, right? Some Turing machine and some string W. And ultimately what it's going to output, because we're reducing to MPCP, is a set of dominoes, right? Because those were the instances of the post-correspondence problem and its variant. But we don't just want to output any set of dominoes, right? What we want to do is we want to output a set of dominoes such that there's an accepting computation here of M on W, if and only if there is a match that starts with the first domino among the set of dominoes we output, right? And so last time we showed this, like we actually showed a Turing machine that computed this mapping reduction, how we were going to compute it. And it did this by sort of adding a set of dominoes so that a matching in some sense corresponded to a valid computation, right? We added the dominoes such that as you concatenated elements onto the potential matching, right? In some sense, it corresponded to verifying that a computation was valid and accepting, right? So, and kind of the intuition for this is pretty clear, right? I mean, at the end of the day, what do you do? What does your human brain do when you're checking a sequence of configurations to make sure that it's a valid computation? Well, you want to, on W, say, of Turing machine M, you want to make sure that it starts with the starting state, that it ends with an accept state, that it starts with the starting configuration, ends with a configuration whose state is the accept state, and that each intermediate configuration I follows from the previous one according to the transition function. But the changes that the transition function makes are really local. And so basically 90% of the work is just making sure that, the overwhelming majority of the work is just making sure that all the other sort of characters are the exact same, right? That aren't around kind of the local changes made by the transition function. And this is exactly what a matching entails, right? Matching these top characters with these bottom characters. So to kind of quickly go over again, and where I'm going with all this is I want to produce a concrete example, like an illustration today, of the construction that we saw in the proof last time. So to quickly rehash, we added this first domino, D0, right? Which is what our MPCP match is going to start with. And it looked like this. There's only one symbol on top, right? There's nothing here, only one symbol on top. And we're going to encode configurations in the way you'd expect using these pound signs as delimiters. And then we add, like I said, a bunch of dominoes corresponding to the process of verifying, so to speak, that would allow a matching to verify to be a matching in some sense, if and only if an accepting computation exists. But this is just empty words, right? Let's actually get to the concrete example, and then the purpose of each of these dominoes will become clear, I think. Okay, if my laptop would cooperate. Oh, there we go. Cool. All right, so the way that we prove this, as I said, was we wanted to show this if and only if for the mapping reduction, right? Where this set of dominoes here is just the output of our mapping reduction. And the way that we did that was we proved that for any computation of M on W, you could construct a corresponding sequence of dominoes that we called script D here, right? From P, with the property that C is an accepting computation if this sequence of dominoes from P, right, over P is a match. Yeah. So our reduction, I just want to clarify a point here. Our reduction isn't constructing this sequence. All it did was output this set of dominoes, right? And what we did in the proof was we showed that for any accepting computation C, right, you can construct this sequence D. And in particular, that construction is what I'm going to illustrate with an example today. Okay? Are there any questions about that? Cool. All right. So let's take a look at an example here. So I'm going to describe the construction in phases, even though we kind of just did it all at once implicitly in the proof that we gave last time, but I think this will clarify things. So the first phase, right, and this remark here just corresponds to what I said a second ago, that what I'm about to do, our Turing machine R sub MCP did not do this. It just output the dominoes, right? What this is an illustration of is the sequence that we construct in the proof to have this if and only if property. And I'm going to use colors to indicate continuous, characters, consecutive characters that are of the same color. You should interpret them as having been added with the same domino, okay? And we're going to construct this sequence of dominoes that corresponds to an accepting computation as we, one kind of step or configuration at a time, all right? I know, all I've done here is I know that we were illustrating the sort of matchings or sequences of dominoes with a top and a bottom before, but I've just kind of flipped things for convenience of representation. And this is going to be our top, and this is going to be our bottom. And what we want is that in each row here, all of these guys is going to match by the end of what we're doing. Okay? So here's, our computation C. It has a starting configuration C0. Maybe it looks like this. Here's where the head is, okay? It's looking at W1, the first character, okay? And this T0, this is just sort of what we called this subsequence in the bottom matching so far in our proof. This is just kind of so that you can then go back and refer to the proof if you have more questions after this is over. Okay, so let's see what the phase of our construction that corresponds to constructing, or the phase of our construction or this sequence that's going to correspond to the first step of computation, right? The first configuration change. So it's going to look like this. Oh, by the way, in C0 here, this big, like same color thing, this was the first domino D0 that we defined, right? Okay, so here, let's say this is the next configuration, or the first configuration after the starting configuration in our computation, okay? And let's say maybe the tape head moves to the right or downwards here in this representation, and it overwrites the character W1 here with U1, okay? Now, we've added dominoes so that sort of at each step here, our matching is going to mimic or simulate, in some sense, the computation that we're doing, okay? So what we're going to do here is, all right, each single, like, as I said before, each of these contiguous blocks of color corresponds to one domino that was added in this matching that we constructed, okay? Or in this set of dominoes that we constructed. So you can see that, like, for individual characters, right? First of all, we've matched everything here, right? We've had dominoes that allow us to do that. But if this is the top of the domino, then because there was this massive chunk on the bottom domino that was so much larger than the top chunk, right, of the first domino, what this is, the way to interpret this is that, for example, this W2 here, which is indicated by purple, comes from a domino whose bottom character ended up over here, right? So you can think of, whoop, this is like what that domino corresponds to. It's a single character, so to speak, right? And you have similar dominoes for each individual character. Every time we match, right, with a W3 here. And what that means is we're going to add a domino that just matches, kind of shifts that character over here because of this displacement. Yeah? And it's the same for each individual we added dominoes for all of these this was step 3 over here, right? This is why we added all these, same thing on the top, same thing on the bottom dominoes. But then we also added dominoes to handle the transition function, right? The changes in our configuration that are going to happen around the transition function. And those look like this. We had one for right transitions and one for left transitions. And so in particular, because there was a right transition from here to here, where we overwrote W1 with U1 and changed from state Q0 to Q1, what that means is we're going to use the domino that corresponds to that possible change that the transition function can make, right? You can see, okay, look, this green domino here, it has Q0, then Q1, but its bottom isn't the same, unlike all these other single character dominoes that we added. It actually reflects the change that happened in our transition function, right? So now where there was Q0, there is U1 corresponding to the movement of the tape head. And W1 has disappeared because it's been overwritten by U1. And we've moved the tape head forwards over here, right? To Q1. To this position in front of U1. And we have updated the state to Q1 from Q0, right? So our matching so far, right, that I claim eventually is going to give us, this is just a sequence of dominoes. I don't know that it's a matching yet because I haven't explicitly said that this C here, right, is an accepting computation. So far, all that we know about C is that it is a computation of M on W, right? But so far, what it's doing is there's like the correspondence between this being a valid sequence or chunk of a computation so far and it being verified, right, by the sequence of dominoes that we've constructed so far should be pretty clear. Yeah? Any questions about this? Any questions about why we're doing this? Because it's one thing for me to sit here and stand here and talk about like just match this character with this character, but do we all see where we're going with this? Yes. What we want to get at the end is that I want, like, you give me, I want to show you how, right now what I'm showing you, this is something that we did in the proof last time. We have that our reduction outputs some set of dominoes P, right, on input MW, okay? And I want to show you that for that P and for that computation C, there's a way of transforming any computation of M on W into a sequence of dominoes, right? Such that this sequence is actually a match if and only if this computation is accepting. Does that make sense? Are we all on the same page about that? Where we're sort of going with this? Yeah? Cool. So, all right. So far, we've shown how to construct this sequence that satisfies this if and only if property up to the first configuration change, right? Let's see what happens when another configuration change occurs. So maybe now, like all of this is the same, right? So far, but like this sort of section here, I've just sort of copied and pasted it over. The action's happening because we've added a new configuration change here, C2, yeah? And maybe what C2 does is it moves the tape head back to the left. It overwrites W2 with U2 and transitions to state Q2 from Q1. Yeah? So we added dominoes to handle left transitions as well, right? And they looked like this. They had this sort of these three things on the top and these three things on the bottom to account for the fact that we are moving the tape head backwards, right? And we had these dominoes for every possible set of characters for which this relationship in the transition function held, right? So how do we use that to sort of extend this sequence of dominoes that we're building? Well, same as before, we're going to use our dominoes that just correspond to making sure all the tape cells far away or not immediate in the immediate vicinity of the transition function don't change, right? So W3 now, it matches with this, but the domino that put this here, its bottom is over here, right? And the same thing for all these guys up to WN, it matches here, but the domino that put this here, its bottom is over here, where this other gray WN is. Yes? And the only other thing that changes is we have this transition domino where it reflects exactly the change that happened here, except now we move back. Q1 transitioned to Q2, the tape head moved back. We overwrote W2 with U2. And so far, it seems that our matching, our prospective matching that we don't know is a matching yet, but is just some sequence of dominoes, has correctly simulated another step of our transition or of our computation so far, okay? And you can keep doing this, right? For every single configuration change that happens, you just keep in this matching that we want to construct, or this sequence of dominoes that we hope to be a matching if this thing, this C here, is an accepting computation. You could just keep adding the appropriate dominoes from our MPCP output. And eventually you'll get to something that looks like this, right? Maybe you made it all the way to like phase. Now, okay, now, mind you, so far, I've said nothing about C, like script C being an accepting computation, right? So in particular, if this is a looping computation, this sequence of dominoes will go on forever and it won't be a match, right? Because a match needs to be finite. So, okay, that's promising for our if and only if. But okay, now let's suppose that C actually does halt, say on step L, and it's an accepting computation. Then we want to make sure that this matching, this just sequence of dominoes so far that we've witnessed is in fact a matching, okay? How are we going to do that? Well, let's see what it'll look like up to the simulation of the elf or final step. So maybe you have all this sort of these transitions that we described, or these configurations that we described earlier, and the corresponding sections of this just sequence of dominoes, right, that we've concatenated. Maybe, oh, okay, you're looking at the second to last configuration and the last configuration CL, which does indeed contain an accept state. And for the sake of simplicity, let's just say that there are exactly 4 non-blank characters in this configuration, okay? A, B, C, and D, with the tape head currently looking at C, all right? Then the sequence of dominoes that we've, like this script D that will have constructed so far is, you know, it follows exactly the same way you'd expect as we were extending it earlier. But there's a problem now, right? What I wanted to do was I wanted to construct a sequence of dominoes that was a matching if and only if this was an accepting computation. So I've witnessed now that this is in fact an accepting computation because I saw the accept state, right? But is this sequence that I've constructed so far a match? Is it? What would it take for it to be a match? We have correctly matched each individual character that we've seen on the top so far, right, with a corresponding character on the bottom. But where is the problem? Any ideas? Perhaps I've gone too fast. Are there any questions about what we've seen so far? Why we were doing it? Oh, I see it. There's a hand. Okay, what's your question? Yeah. So this, oh, damn, is one domino, right? I'm using colors to indicate the matching of dominoes. Yeah? But this isn't a domino, right? This thing here, this is just to illustrate that we've added a domino over here, right? That has made this a partial matching, if you will, so far, right? But like where these characters on the bottom came from was from a previous domino that's not shown here that I added, right? Yeah, the problem is this big blank space, right? Because in order for it to be a matching, we need every character on the bottom to match with the character on the top, not just the characters on the top that we've seen so far. But there's nothing here. Our bottom is longer, right? And that's but we want this to be a match because, like I said, we've witnessed an accepting computation. So how do we fix this, right? Well, the way we'll fix it is this is where those extra dominoes that I think confused a lot of people came in last time. Those dominoes look like this, right? So I think I called them annihilator dominoes. And the way they look is, you'll notice they're actually the only domino with more characters on the top than there are on the bottom, right? And it looks like for every single character in our tape alphabet, we'll add a domino that looks like A, the accept state, and just the accept state on the bottom, and the analogous thing with A on the right instead of the accept state on the top. Now, why are these going to help me get my match, like my sequence of dominoes so far that partially matches all the way to a full matching? How are these going to help me? Well, what's going to happen is that we can now pad our matching with these extra dominoes that I just described. And this doesn't correspond to simulating any more of the computation. We've seen that it's an accepting computation, and we have a partial match so far. All the additional dominoes that we're going to add now in our script D are just going to be so that we get an actual matching. And how are we going to do that? Well, what we can do is, if this is, what I illustrated before, notice that the difference between the bottom and the top here, right? The bottom and the top here was 7 symbols, right? There were 7 more symbols over here that we wanted the top to catch up to, so to speak, right? And that's where these annihilator dominoes are going to come in, because we're going to add them one at a time to shrink the relative length of the bottom, like the length of the bottom relative to the length on the top. And how are we going to do that? Well, look, so this is what we had before. And now we're going to add another set of characters that does not correspond to any computation, because we're done simulating. We've seen that it's accepting, such that we use this annihilator domino in orange here. You'll notice that A matches to A, B matches to B, right? Or sorry, this is a domino that we've added here to match this A to this A, okay? And this B belongs to a domino here that we've added to match this B to this B. And now what we can do is we can add this domino in orange here that basically allows the Q accept to eat up this C. Because you'll notice that C is missing now, right? But then we can still add that domino of 2 Ds to match this D to this D and the rest of the guys, yeah? And now look, we've shrunk the difference by 1. Now the difference between the bottom and the top is 6. And so you can just keep using these annihilator dominoes to keep eating a character on the bottom every single time until finally, right? Like we can do it again here using the other annihilator domino that ate the character behind it, right? Where, okay, we've added this domino AA to match to the A. And this is the annihilator domino that we've added over here now, because you can see the B on top has disappeared. It's no longer present here. And the gap has gotten a little smaller. Now the difference is of, the difference between the lengths of the top and bottom is 5. And you just keep doing this, adding one, using one annihilator domino in each like pseudo configuration that you're simulating until after 6 times, because, there were like our starting gap was of length 7. What you'll end up with is just this, right? The length of the bottom or the length of the top will finally catch up to the length on the bottom. And all you'll be left with is this final matching, this trivial sort of set of delimited characters where the pound matches to the pound, Q accept to Q accept, and the pound matches to the pound. Yeah? So we just kept applying these annihilator dominoes until the difference in length was 0. And at that point, we knew that our sequence of dominoes, which partially matched, is now a full match. Okay? Are there any questions about this? Like why we did anything that we did, what the purpose of anything was? Is there anything that you can point out where you're like, I'm not sure why we needed to do that. I think we could have gotten away without doing that. Is there anything like that? Or are we all sort of on the same page with this? Let's see, the time now. Okay. So I wonder if I can do this at this point. Yeah, I think what I'll end up doing is I'll call it quits here. And the only sort of part that's left, that's remaining, is, okay, we showed that MPCP was undecidable, but that's not what we wanted. We wanted to show that PCP was undecidable. So how are we going to do that? Well, we're just going to give a reduction from MPCP to PCP. And I think I'll just upload this like in a lecture recording, and then you can look at it there. But the kind of significant, like the big question is like, why did we need MPCP in the reduction from ATM instead of PCP? Like, why couldn't we have just, like, why couldn't we have just constructed, called this thing, like this P that we output here, a PCP instance at the end of the day, instead of an MPCP instance? Yeah? Yeah, exactly. We wanted it to start with the start configuration, and it better have, because we added dominoes that looked like this, right? So you would have gotten a trivial matching no matter your input of just the top thing and the bottom thing. You know what I mean? And you could just ignore everything else. So this is why it was important that we used MPCP instead of PCP. And what I'll upload probably later today or something is the rest of kind of getting all the way to PCP being undecidable. All right, so let's actually wrap up the proof that PCP is undecidable now by giving a mapping reduction from MPCP to PCP. Now, let's do a little bit of brainstorming first. What we want to do in giving a mapping reduction from MPCP to PCP is we want to come up with a Turing machine that's going to compute some function such that on input an instance of MPCP, it will map it to an instance of PCP that I'll call P prime, such that there is a match in this MPCP instance, meaning it starts with the first domino, so it's an MPCP type match, if and only if there is a match in the PCP instance, meaning it can start with any domino. Now, let's do a bit of brainstorming, and in the process, perhaps illustrate why this is, at the very least, non-trivial. So let's suppose that P is my MPCP instance, as I just said, and its first domino is D0. And we'll assume that each domino looks like this. It has a bunch of sort of symbols on the top here, with the string SI. This is the third symbol in that string. And then it'll have this bottom string TI, and each of its symbols in that string will be over here like this. So, okay. As I sort of just mentioned, kind of the crux of what we're hoping to do here is we want to transform this MPCP instance into a PCP instance, P prime, such that P, this MPCP instance over here, contains a match starting with D0 if and only if this new set of dominoes, P prime, that I'm going to construct contains a match starting with anything. It's an if and only if. And really, the only if is the challenge here, right? Because if I have a matching starting with domino D0, excuse me, in P, obviously I have a matching starting with any domino in P prime. In particular, it's just that matching starting with D0. So, okay, well, maybe then, given that that's the case, can our mapping reduction just do the dumbest possible thing and be sort of the identity? Can we just, on input P, output P again? Like, would this be would this have the if and only if properties that we're looking for in our mapping reduction? And the answer is no. And the problem is that P could contain a match that starts with something other than D0, meaning it would not be an instance of MPCP. Oh, sorry. So the issue is that P, it could be the case that it has no match starting with D0, so it's not an instance of MPCP. However, it does contain a match that starts with something other than D0, in which case it would be an instance of PCP. And that's not what we want. We want that if and only if, right? Okay, so it seems we need to do something a little more clever. Well, maybe there's a way that we can just kind of modify each domino that we have in P in such a way that we can kill off any matching over P that starts with a domino other than D0, but preserves any matching that starts with D0, right? So now we still get kind of the nice if property of this stupid idea, but we avoid this problem over here with the only if. So, all right, maybe there's some way that we could do that. In particular, let's suppose that we have some matching M0 that starts with D0 over my set of dominoes P. And let's suppose that we have another matching M1 that starts with some D1, that is not equal to D0. Now, and let's suppose maybe they look like this. If we kind of illustrate the first two dominoes in each of these matchings over P, we have sort of that this is the domino D0, this is the domino D1, this is some, next domino DI, and this is some next domino DJ in M1 over here. Let's suppose they look like this. Now I want to modify my dominoes, right, in such a way that in whatever way I transform them, if I substitute them back into M0, then this M1 here is no longer a match, right? I've kind of killed it off, but M0 survives as a match. And a really simple way that we can force this to happen, maybe, is what if we just modified it as follows? So for each of my original dominoes, DI other than D0 and P, where, again, DI just sort of looks like this, what we're going to do is we're going to add a new domino, DI prime, to my PCP instance that I'm constructing, P prime, which modifies my original domino DI as follows. So it looks pretty much exactly the same way my original domino does over here, but I've added two symbols. I've added a dot here, where this dot can sort of be any symbol it's not already a symbol. It was in my original PCP instance. And I've shifted everything on top over, kind of, so to speak. And then I've added another dot over here on the right bottom, right? Okay, now why have I done this? Well, the other thing that we'll do is, sorry, this is a typo. This should say D0 prime, is okay, we've shown how to modify every domino DI other than D0 in my new instance. So the way that we'll construct our modified D0, which we'll just call D0 prime, is it will have two dots at the beginning and one dot on the lower right symbol. So why have I done this? Well, it isn't hard to see that if I have any matching over this new set of dominoes, P prime, right, the modified set of dominoes, it has to start with D0. Why? Because I've added a symbol dot other than the first symbol on the bottom to every other, every domino DI to turn it into DI prime other than D0, none of these other dominoes can be the first domino in a match, right? D0 is the only possible one because it's the only domino where the first symbol on the top matches the first symbol on the bottom. So, okay, let's see how that transforms those matchings M0 and M1 that we were talking about earlier. Well, if we just substitute in these new dominoes DI prime everywhere where there was a domino DI in these original matchings to obtain some new matchings M0 prime and M1 prime, then what we end up with is this, right? So our original matching M0 prime seems to still be a matching, right? We have that the first symbol on the top matches, or the first symbol on the top matches the first symbol on the bottom. And then because, there's this extra sort of dot that juts out on the bottom for each of these DIs, then it can kind of interlink, so to speak, with the extra dot that we've added over here at the top and form a match that way. And then the rest of this domino seems to match an exact, the rest of the matching here seems to be the exact same as it was in the original M0 before we made the modifications. And we can see that we've successfully killed off our M1 prime now, right? Because, I mean, exactly as I said, this dot here, it doesn't match the first symbol on the bottom. Okay, wow, nice. So are we done? We've successfully killed off M1 prime as we wanted as a matching over P prime. But what we wanted to make sure was that we preserved M0 prime as a matching, right? Because M0 was a matching originally over P, and we want to still make sure that M0 prime is still a matching over P prime. Now, is that the case? Well, it turns out that it's not, for a really silly reason, kind of, because of what happens at kind of the end, which we didn't illustrate here because we kind of just assumed, we didn't illustrate. We only sort of looked at the first two dominoes in this sequence M0. But if you if we were to assume that those first two dominoes were the entirety of the match, right? If M0 consisted of only domino D0 followed by domino DI, then what we see, the kind of problem becomes very clear, right? Because where we successfully match on the first sort of domino, and then we match on this little overlapping portion of dots, right, on the DI prime that we construct. But the issue is that, well, this extra dot that we had jutting out in the DI prime to match with the extra dot on the top that we had for future dominoes, right? That just kind of sticks out on the last domino without another dot on top to match it, right? So we've ruined, so to speak, the fact that M0 is a matching. And we're going to have to fix this. How do we do that? Well, there seems to be a very simple fix. We could just add another domino to P prime, which just consists of two dots on the top and one dot on the bottom. And then we can just tack this onto the end of any matching where this imbalance at the end occurs, right? Because then we have three other dots that allow us to fill out the matching. And so in particular here for M0 prime, we can see that doing precisely that gives us a matching again. All right, so are we done? Have we finally managed to construct a PCP instance P prime such that this if and only if condition that we're chasing after in the mapping reduction holds? Well, there's one final problem, and it's a bit more subtle, and it has to do with the perhaps dishonest way that I've been representing my dominoes so far, which is that I said that each domino here had KI symbol, like the domino DI has KI symbols on the top and LI symbols on the bottom, but those don't necessarily need to be equal in length, do they? As they would appear from this particular depiction of M0. In fact, it's possible that maybe for the domino DI, the top is way longer than the bottom, right? In my matching M0. And for D0, the top is way shorter than the bottom, right? I mean, that doesn't rule out the possibility of a match in my original instance, just because these sort of overlapping, like the portion of the bottom of D0 that juts out and the portion of the top of DI that juts out can match with each other to still even out the lengths by the end of it, right? But this sort of implicit assumption that we've making that the length on the top and the length of the bottom, that kind of screws us over when we start adding dots in the way that we've been suggesting. Why? Why does that happen? Well, let's see what happens if M0 looks like this, and we try constructing the PCP instance P prime in the way that we've suggested so far with the dominoes that we've added so far. So what we'll end up with is if my M0 looks like this, my M0 prime that I get by substituting my new dominoes is going to look like this. So I'll add the 2 dots in the beginning, and then where this was kind of the bottom of my domino D0, I'm going to add a dot over here, right? And now in my new domino, in my domino DI prime, where this was the top, we add a little extra dot over here in the leftmost portion, which was intended to match with this dot that jutted out from the bottom of the previous domino. But as you can see, it very clearly doesn't. And that's kind of the heart of the problem, right? Is because here in the matching of M0, we had S1 was matching with K0 plus 1, right? But in adding this dot now, we've shifted everything over to the right such that now, whereas S1 or SI, S to the I1 was matching with T0 sub K0 plus 1 before, as in over here, now, everything's slanted over and we're not matching necessarily anymore because S1 is on top of the character to the right over here. And this kind of right shift that was introduced by this dot potentially ruin this entire portion of the matching over here until we add this domino or this sort of dot at the end of the bottom of D0, and we go back to the actual matching or the portion of our sequence M0 where we were matching again, right? We had this symbol over here matching with T1, and we can see that after we added the dot so that the kind of bottom shift catches up with this right shift that we introduced by adding this dot, we're matching again. So this region over here no longer matches because of the dots that we've added. And so we need to fix this. So how are we going to fix this? Well, what we need to do is we need to accommodate for the possibility that these sort of overlaps, the difference between the top length and the bottom length, can introduce a dot anywhere, sort of in this overlapping region between the top and the bottom. And so the very sort of simple fix to that is, rather than just adding the dots at the start of the top and the start of the bottom and the end of the bottom, and as we've been doing so far, we'll just add dots between all of the symbols in all of our dominoes. So what do I mean by that? Well, if D0 looked like this before, right? What D0 is going to look like now is we add the 2 dots in the beginning as we did before, but as you can see, we've also added dots between every single symbol on the top and every single one on the bottom. And we do the same thing with SI or DI prime, right? The modified version of DI and all our other dominoes. And the reason why we've done this is so that, looking at this original match, right, we can see that S1 to the I matches with T0 to the K0 plus or sub K0 plus 1. And the issue that we were experiencing before was that the introduction of this dot shifted the top to the right in a way that displaced the matching of S1 to the I with T sub K0 plus 1 on the bottom, right? So the fact that we now have an intermediate dot over here between every single symbol means that when we add this dot on the top, we are no longer introducing a shift that ruins this portion of our match, right? Because now we have a dot on the top and a dot on the bottom. And so we're matching again, right? You can see that S2 matches with K0, T sub K0 plus 2. That happens over here. These guys match over here. They match over here. These guys match over here. They match over here. And you can see that in this way, we've preserved our match, right? And the reason kind of why we add dots between every single symbol is because these sort of pathological overlaps, right, that introduced these shifts that ruined our matching could kind of occur anywhere, depending on the domino that follows D0 in this example. Like here it was DI, but it's, you know, it's not inconceivable that maybe there was some, our DI was something that didn't even cover the entirety of the top, right, of this jutting out bottom portion of D0. And then we would have to add another domino over here. And so these sort of splices that take place with the dots can potentially occur depending on the way that the rest of our set of dominoes is structured, really anywhere. And so to accommodate for the fact that this shift can take place anywhere, this pathological displacement, we've added dots between every single one of our symbols in our dominoes. And I claim that this is finally idea number 4. This is in fact the idea that works. This is how we're going to, this type of modified domino, this is with the dots between everything and this extra guy on the end, sort of the way we had before. This is going to be the PCP instance that actually gives us the reduction that we want. Okay, now let's see the proof, now that we've seen the idea and the motivation. So we're going to define a Turing machine F that'll compute our mapping reduction from MPCP to PCP. So what that means is it'll receive as input an instance of MPCP, and we're going to construct an input or an instance P prime of PCP in exactly the way that we just brainstormed, okay? So we'll set it to empty at the beginning, and then if D0 is the first domino in P, then we're going to modify it in this way that we described earlier by adding a dot between every single symbol, and it will be the only symbol such that the first two, like the first symbol on the top matches the first symbol on the bottom. And for every other domino, we'll do something similar. We'll add dots between each guy, but unlike D0, we don't add this dot at the beginning. And this forces any match to start with D0 in my general PCP instance, P prime. And lastly, we add this domino to account for the final sort of dot jutting out at the end of any new matching. And yeah, I claim that then we just output P prime and that is the PCP instance that we're looking for. So, okay, let's prove that now. We claim that F computes this mapping reduction that we want, right? And what that means is that our input MPCP instance P contains a match if and only if this output here that we've constructed, this contains a match that starts with D0 if and only if this output instance P prime that we've constructed contains a match that could potentially start with anything, right? And yeah, this P prime is exactly the output of this Turing machine F that we described. So let's prove the forward direction now. Let's suppose that P is in fact in MPCP, meaning it contains some matching M0 starting with D0. And let M0 prime be exactly this sequence obtained from M0 by just swapping every DI with the DI prime that we constructed, and then adding this extra domino to the end. So if we look at all the symbols that are in our new matching M0 prime, they are of one of two types, right? Either they are a symbol that was already in M0, or they are one of these dots that we've added, right? And you can verify that for every single one of the symbols that was originally in M0, it's going to match with exactly the same symbol that it did on the bottom in M0 in this new instance, M0 prime. And that was because of the fact that there's this kind of, like, these dots are just preserving the structure of the mapping, so to speak, because they occur between every symbol, right? And because every other symbol is a dot, we know that all of those dot symbols that didn't appear in M0 also have to match with each other, right? So then everything in M0 prime matches and we're good. M0 prime is a match over P prime, right? And therefore P prime is an instance of PCP. But now let's look at the only if direction. And this direction corresponded to, well, if we have a match M0 in PCP that starts, with D0, we want to make sure that we preserve it as a match in this new instance P prime. And so this only if direction will correspond to, well, I want to kill off any potential match in my MPCP instance that doesn't start with D0, right? So let's suppose now that M prime is a match over P prime. Because P prime is a PCP instance, it could start with anything. So since D0, or I suppose this should be D0 prime, in fact, is, as I've noted earlier, the only domino in P prime where the first symbol on top, that dot, is the same as the first symbol on the bottom, that other dot, we know that M prime has to start with D0 prime. And so by removing, you can just kind of remove all the dots in between all your characters in M prime, right? And that induces a match over P, starting with D0. And therefore, P has to be in MPCP. It contains a match. Yeah, and when you combine, okay, so this concludes the proof of lemma 5, right? That MPCP mapping reduced to PCP. And what we proved last lecture was that MPCP was undecidable. Therefore, when you combine these two facts, you get, at long last, that PCP is undecidable.